Hi everyone, and welcome to our last screencast for Unit 1. Today we're going to be talking about buffers. Now we know that living systems prefer to keep their pH between about 6 and 8. Because we're mostly made of water as living things, the pH level, how acidic or how basic we are, is going to affect all the reactions that happen in our body, and thus it's going to affect our health. If you have a pH imbalance for a really long time, the body doesn't tolerate it very well. So your body has all these regulatory mechanisms to help balance the pH, and it does that by removing as many acids from the body as it can. But sometimes that's not enough and the pH does become too acidic or too basic, and cells will really just get poisoned by their own toxic waste and die. Just like acid rain can destroy a forest, if your blood is too acidic, it can eat through body tissues like veins and arteries, and it'll corrode everything and put holes in them. So if left unchecked, an imbalanced pH will interrupt all sorts of things in your body, everything from your beating heart to how your brain fires. And lots of times this will go unnoticed and undetected for quite a while, but if it progresses, it can lead to many different degenerative diseases. So for example, heart disease, cancer cells actually really love acidic pH environments, and so if you have an acidic pH, it'll be more likely that you will get cancer. If you have an acidic pH for a long time, another really interesting thing it does is it can trigger an insulin sensitivity. Basically what that means is more insulin is released, and your body will grab onto every single calorie it can and turn it into fat. And it's no surprise then that acidic pHs are also related to diabetes. In humans, our blood pH, we try to keep it around about 7.46. That's slightly basic. That's considered optimal. And like I say, our bodies have all these different mechanisms to try to keep it at about 7.46. And many other tissues in your body like a different pH. The stomach enjoys a pH of about 2.5. The vagina needs a very acidic pH to ward off invaders, maintaining a different pH in different parts of the body. And mostly it does that through buffers. So we talked in the last screencast about adding strong acids to water. If you add a strong acid to water, the pH changes drastically, and that's because are released into the water, they release hydrogen ions when they dissociate from their partners. And that's because when you release acids into water, as we talked about HCl last day, as soon as it hits the water, it will dissociate into hydrogen ions and whatever else that hydrogen ion is attached to in an acid. More hydrogen ions gives you a more acidic solution, and the pH will drop drastically. What a buffer is it's a chemical that can resist the pH from changing. And so if a buffer is in an acidic solution, the buffer will actually take those extra hydrogen ions and absorb them. So a buffer can absorb hydrogen ions.
Established that in a strong acid solution, there's too many hydrogen ions. So we want to try and buffer that. So if you add a strong acid to a solution that has a buffer, the buffer will be attracted to the hydrogen ions, and it will steal them out of the solution and stick them onto itself. So we're looking at this as an example, CO3 2 negative. It's got 2 negative charges, and it's those negative charges that will be attracted to the positive hydrogen. And so the positive hydrogen will be attracted to this negative carbonate, and it will basically stick to it, form a bond to it, and will become HCO3 negative 1 now because it's lost a negative charge because it's joined with a positive ion. The hydrogen will get absorbed by a buffer, and the pH won't change. If a buffer is in an acidic solution, it will absorb or grab onto all the hydrogen ions and remove them from the solution so the pH doesn't change. Now we already talked about how a strong base, when it's added to water, will disassociate and release hydroxide ions into a solution. So if you look at these NaOH molecules here, as soon as they hit the water, they will separate from each other into the OH ions and Na ions. You see they've all done that as they've hit the water. Now what that does to the pH is it makes it more basic. It will increase the pH, make it more alkaline. The pH will go up 9, 10, 11, and will keep increasing. Now you don't want that to happen
fluid that will resist changes in pH. Now, with a basic solution, our buffer is going to do the opposite of what it did with the acidic solution. It's going to give the base hydrogen ions. It's going to give away its hydrogen ions to the base. And what those hydrogen ions will do is they will join to the OH ions from the base to make water. That neutralizes the solution so the pH won't change. Let's look at how that exactly happens. So if you have a strong base, too many hydroxide ions, the buffer is going to give away its hydrogen ions, that hydroxide ion. So let's look at this buffer HCO3 -1. And you'll see that in this buffer, there's lots of hydrogen ions that the buffer can give away. Ions to the hydroxide, water. HOH is just another way of writing water. What you're left with then, what's given away with a hydrogen ion, is you're left with HCO3 -1 this time instead of, because it's given away one of its positive ions, it's become negative. So the OH gets turned into water, the base is neutralized, the pH doesn't change when it's in a buffered solution. So in a basic solution, what a buffer will do is it will give away as many hydrogen ions as it can to make sure that the pH does not change. So what you should know is that a buffer, we've been talking about different buffers, but a buffer usually has more than one version of itself. You can see this buffer has 3 versions of itself. And when it's in an acidic solution, what happens is this negative version of the buffer is attracted to positive hydrogen ions from an acidic solution. And when you add a hydrogen ion to CO3 negative, it becomes HCO3 -1. It's still negative, you can still attract one more positive hydrogen ion, and when it does that, it becomes H2 now. Now it's got 2 hydrogen ions stuck to it, CO3. It's not negative anymore, so it can't attract any more hydrogen ions, and we call this overloaded. If you keep adding more and more acid past this point, the pH will decrease, and the buffer is overloaded. It can't do its job anymore. So in an acidic solution, the buffer is overloaded. In a basic solution, you see this form of the buffer has hydrogens to give away. It's going to give 1 hydrogen away to hydroxide ion from the base to make water. pH is neutralized, it doesn't change. It gave away 1 hydrogen, so now it becomes only 1 hydrogen HCO3 negative. It has 1 more hydrogen to give away, so it'll give another one away to the next base. Water, again the pH is neutralized, doesn't change, but now we become CO3 negative. There's no hydrogens left to give away, so in a basic solution, this buffer is diluted. And we'll run hydrogen giveaway. The buffer can be overloaded if there's too much acid or too much base, because eventually all the buffers are used up. And a buffer can either donate hydrogen ions or accept hydrogen ions as required. The most important buffer that we're going to talk about this week is the bicarbonate ion, and we find that in the blood. Looks like this. This is the bicarbonate ion here, and we'll learn a lot more about that when we talk about the respiratory system. Make sure you come to class with your hot questions all about buffers.